A cosmic engine more powerful than a billion suns hides at the center of nearly every galaxy. These are supermassive black holes, and their existence so early in the universe presents a profound mystery that shakes the foundations of modern astronomy. How did these giants, weighing billions of times our sun's mass, appear fully formed when the cosmos was just an infant? In our journey together, you will discover the 5 competing theories scientists are using to crack this cosmic code, from unimaginable feeding frenzies to collisions of dark matter. We will explore whether they grew from primordial super seeds or if they broke the known laws of physics to consume matter at impossible rates. The answer reshapes our entire story of cosmic evolution. What does the incredible speed of these giants suggest about the fundamental rules of our universe? The infant universe was a place of strange and impossible giants. When our cosmos was only 700 million years old, quasars blazed with the light of 1 trillion stars, all powered by supermassive black holes that had no right to exist. The sheer scale of this timing problem defies common sense. Think of a baby just a few months old, already standing 6 feet tall. This is the astronomical equivalent, a cosmic growth spurt so extreme it seems to break the rules. At the heart of this mystery lies a fundamental speed limit for black holes, known as the Eddington limit. This is the maximum rate at which a black hole can steadily pull in matter. As material spirals inward, it releases immense radiation which pushes back against the incoming gas and dust. It is a natural balancing act, a cosmic diet that prevents a black hole from binge eating. Yet, to reach 1 billion solar masses so quickly, these early black holes would have needed to consume matter at or above this limit for their entire existence, a feat as unlikely as holding your breath from infancy to adulthood. Telescopes like Hubble and the James Webb Space Telescope have only deepened the mystery, spotting more of these impossibly mature objects the further back they look. This timing paradox is not a minor puzzle. It is a direct challenge to our understanding of how the cosmos built its first structures. It forces a profound question. Did we misunderstand how black holes feed, or are we missing a completely different starting point for their creation? This fundamental problem is the driving force behind the extraordinary theories we must now explore. Their staggering scale defies simple definition, for these are not the black holes born from a single star's dramatic collapse. Imagine a stellar mass black hole as a single, dense mountain. A supermassive black hole would be the entire Himalayan range, a continent-spanning entity of unimaginable gravity. While a typical black hole might weigh a few dozen times our sun, a supermassive black hole contains the mass of millions, even billions of suns, all crushed into a singularity at its heart. This incredible density creates an event horizon so vast it could engulf our entire solar system and beyond, a point of no return where not even light can escape its grasp. These cosmic monarchs do not wander the galaxy, they rule from the center, acting as a gravitational anchor for the billions of stars swirling around them. Our own Milky Way has its own quiet giant, Sagittarius, a star, a silent testament to this universal architecture, but their influence is far from passive. Through immense gravitational tides and the blazing energy of infalling matter, these giants can either spark star birth across a galaxy or snuff it out entirely, their power echoing across cosmic time. This deep connection between the invisible heart of a galaxy and its visible structure is why their sudden appearance in the early universe is so baffling. How do you detect an object that emits no light of its own? Astronomers rely on the ghostly footprints these giants leave on their surroundings. By tracking the frantic orbits of stars whipping around an empty point in space, they can measure the mass of the invisible predator hiding there. When a black hole actively feeds, the story becomes even clearer. As cosmic gas and dust are pulled into the accretion disk, the material is heated to millions of degrees, blazing with light across the electromagnetic spectrum before vanishing forever. This process creates a quasar, a beacon so brilliant it can outshine every star in its host galaxy, a lighthouse shining from the edge of time itself. It is through these brilliant, violent meals that we can spot the youngest supermassive black holes, their incredible brightness betraying their impossible presence in the infant cosmos. These brilliant beacons of light, however, are just one way to find the invisible. Sometimes the most compelling evidence is written in the silent, graceful dance of the stars themselves. At the center of our own Milky Way, astronomers have tracked individual stars for decades, mapping their paths as they whip around an utterly dark and empty point in space at speeds exceeding 3 million miles per hour. Their frantic orbits are the only testimony needed, revealing the presence of a hidden titan with the mass of 4 million suns, our own Sagittarius A star. This method of celestial choreography, watching stars trace the gravitational signature of an unseen partner, has now confirmed that nearly every large galaxy has its own dark heart. But what about collisions, the moments when these giants themselves are shaken? A new window onto the cosmos has opened with the detection of gravitational waves, the ripples in the fabric of spacetime itself. Observatories like LIGO and Virgo have listened to the faint echoes of black holes merging, a cosmic shudder that travels across the universe. While current technology mainly hears the lower-pitched waves from smaller black holes, future missions are being designed to tune into the deepest frequencies, the rumbles that would come from the mergers of the supermassive giants themselves. And then there is the most direct portrait of all, the now famous black hole shadow. Using a global network of telescopes working in unison as an Earth-sized eye, scientists have captured the outline of a black hole's event horizon, a dark silhouette encircled by a ring of fiery light from its accretion disk. This is not a photograph of the black hole itself, but of its shadow against the glowing background, a ghostly imprint of the point of no return. Each of these techniques acts as a different sense, allowing us to perceive a creature that defies conventional sight. The light from quasars shows us their most violent feasts. The motion of stars reveals their quiet, dominating presence. Gravitational waves let us hear their cosmic crashes. And their shadows give them a face. Together, they build an undeniable case for a universe teeming with these gravitational monsters, a realization that only deepens the central mystery. If they are everywhere and have been since the very beginning, then how did nature become so incredibly efficient at building them? But this natural speed limit creates an immense problem of time. If a black hole started as a simple stellar corpse and fed at this maximum sustainable rate, it would take roughly 800 million years to reach 1 billion solar masses. Yet the universe presents us with these exact giants when the cosmos itself was only half that age. The math simply does not add up. It is like being given a complex recipe that requires hours of simmering, only to find a perfectly cooked meal ready in mere minutes. The standard model, for all its elegant logic, cannot account for this shocking cosmic efficiency. A deeper issue lies in the fuel supply itself. To sustain even this maximum rate, a constant, vast river of gas must flow directly into the galactic center for hundreds of millions of years without interruption. Galaxies are turbulent, chaotic places where supernova explosions and stellar winds can easily push potential fuel away, starving the central black hole. The idea of a perfectly efficient, uninterrupted gas pipeline to the core for such an immense span stretches credibility to its breaking point. These are not minor inconsistencies, they are fundamental flaws in the conventional story. The quiet, steady growth we once envisioned is insufficient to build the leviathans we observe in the dawn of time. This stark failure of the standard model is the very reason astronomers were forced to look beyond the known, toward growth mechanisms that are far more radical and extreme. One theory offers a radical shortcut to this cosmic growth problem. What if these giants never started small at all? The first competing idea suggests that supermassive black holes were born large, emerging from the primordial chaos as ready-made superseeds. This is the concept of direct collapse black holes. Forget a star dying and leaving a small remnant. Picture instead an immense cloud of pure hydrogen and helium, a primordial giant containing the mass of tens of thousands of suns. Under the right conditions, this entire cloud could collapse under its own weight in a single, catastrophic event. There is no spark of nuclear fusion, no brilliant star born to light up the cosmos. Instead, the gas falls inward relentlessly, bypassing star formation entirely and condensing directly into a massive black hole. This is not a slow and steady diet. It is a single, monumental birth that provides a colossal head start. For this to happen, the universe had to be just right. The gas cloud needed to be pristine, completely free of the heavier elements we call metals. These elements, forged in later generations of stars, help gas clouds cool and fragment into many smaller stars. Without them, the cloud remains a single, coherent entity, massive enough to collapse as one. An intense bath of ultraviolet radiation was also crucial. This radiation would have kept the hydrogen in the cloud from forming molecules, which also prevents the fragmentation that leads to a cluster of small stars. Finally, the cloud itself needed to be relatively calm, with very little inherent spin. Too much rotation would have flattened the cloud into a disk that could never collapse directly into a black hole. These specific and rare conditions might have existed only in the most massive dark matter halos of the early universe, creating the perfect cosmic cradles for these instant giants. This theory elegantly sidesteps the timing paradox. A black hole born with a mass of 20,000 suns has a much shorter journey to 1 billion solar masses. It can grow at a more relaxed, sustainable pace, easily reaching its observed size within the narrow window of the early cosmos. The hunt is now on for the ghostly signatures of these primordial seeds. Astronomers scrutinize the properties of the most distant quasars, looking for clues in their light and their host galaxies that might point to this explosive, direct birth. Did the universe itself provide a cheat code, a way to build its most powerful engines almost instantly? But what if these cosmic giants did not need a special birth, but instead possessed a monstrous appetite? The second competing theory dares to ask whether black holes can temporarily shatter their own dietary rules, entering a state of cosmic gluttony known as Eddington accretion. Forget the steady diet, imagine instead a feeding frenzy. During periods of extreme chaos, such as the violent merger of two young galaxies, vast reservoirs of gas can be suddenly and violently funneled directly toward the central black hole. The resulting torrent of matter is so dense, so overwhelming, that it could overwhelm the very mechanism that normally limits its growth. In these extraordinary conditions, the intense radiation produced by the infalling material might not be able to push its way out. The accretion disk becomes incredibly thick and opaque, like a blinding cosmic fog. This trapped radiation cannot exert its outward pressure, allowing far more matter to slip across the event horizon than the standard rules would ever allow. Alternatively, the system might vent the excess energy through narrow, powerful jets erupting from its poles, like a pressure valve on a cosmic boiler. These focused beams of energy blast away into space, carrying off the problematic radiation and allowing the black hole to gorge itself in relative peace. Sophisticated computer simulations of these chaotic events reveal their incredible potential. A black hole starting from stellar mass could, through a series of these repeated super Eddington feasts, balloon into a supermassive titan within just a few 100 million years. This theory transforms our view of black hole growth from a stately, regulated process into something far more dynamic and violent, a cycle of long fasts punctuated by brief, epic binges. The lingering question for astronomers is one of frequency. How common were these extreme galactic conditions in the crowded, turbulent nursery of the early universe? Could enough black holes have found enough fuel for enough of these frenzied meals to account for the vast numbers of quasars we see? The search is on for observational evidence of this super Eddington state, looking for the unique fingerprints in the light of distant quasars that would betray a black hole in the throes of an impossible feast. A third possibility emerges from the chaos of the early cosmos, where growth is not about feeding but about a relentless series of unions. This theory proposes that the first supermassive black holes were assembled piece by piece through a rapid-fire sequence of collisions. In the crowded conditions just after the Big Bang, the first proto-galaxies were much closer together, constantly crashing and merging in a grand hierarchical dance. Each time two of these small galactic building blocks combined, their central black holes were dragged along, eventually spiraling toward each other to form a single, more massive object. Imagine a snowball rolling down a hill, gathering more snow with each revolution. Over time, a series of these mergers could, in principle, build a gravitational titan from many smaller pieces. The recent dawn of gravitational wave astronomy offers tantalizing support for this idea. Observatories have now heard the faint chirp of stellar mass black holes merging, proving that such cosmic unions are a reality of our universe. Scaling this process up, however, presents significant hurdles. The central challenge is delivery. How do you ensure that two black holes, each a gravitational anchor in its own right, actually meet at the center of a new, larger galaxy? Their intricate dance is fraught with gravitational pitfalls. During a close three-body interaction, one black hole can be violently flung away into the void, a cosmic slingshot effect that robs the growing core of its mass. For a merger to succeed, something must slow the black holes down and rob them of their orbital energy, a process that may require a dense background of stars and gas to act as a gravitational brake. This merger pathway finds compelling, if indirect, evidence in the patterns we see in modern galaxies. Astronomers have spotted what appear to be dual-active galactic nuclei, two brilliant engines shining from a single galaxy, likely on a slow, inevitable collision course. Furthermore, the tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole suggests a shared history of growth, where the galaxy and its dark heart assembled themselves in tandem through repeated mergers. This bottom-up approach represents a fundamentally different vision of creation, one of relentless, violent assembly rather than a singular birth or a solitary feast. It asks us to consider whether the largest structures we see are not born but built through a billion years of cosmic collisions. Yet another theory ventures into the realm of the truly invisible. What if the key to this cosmic growth lies not with the matter we see, but with the mysterious substance that makes up most of the universe's mass? This fourth competing idea delves into the possibility of dark matter itself acting as a hidden engine for black hole growth. We know that dark matter far outweighs normal matter, forming vast, invisible halos that cradle every galaxy. This speculative theory asks whether certain types of dark matter particles could be drawn into the intense gravitational well of a black hole, providing a secret, additional source of mass beyond the gas and dust we can observe. One compelling model suggests that if dark matter has specific self-interacting properties, it could behave in a surprising way. Instead of being evenly distributed, these particles might collapse under their own gravity, forming an incredibly dense core right at the very center of a galaxy. This dark matter seed could then act as a direct foundation, a hidden scaffold upon which a supermassive black hole could rapidly build itself, feeding on this invisible reservoir far more efficiently than on ordinary matter alone. An even more radical proposal suggests that some of the dark matter itself might be made of countless primordial black holes, ancient relics from the universe's first moments. In this view, the supermassive black holes we see could have grown by consuming these smaller, invisible cousins, a silent feast in the dark. While evidence for dark matter-driven growth remains highly limited and the subject of intense debate, this line of thinking is profoundly important. It connects two of cosmology's greatest puzzles, the nature of dark matter and the origin of supermassive black holes, into a single, grand mystery. It forces us to confront the possibility that our entire understanding of fundamental physics is incomplete, and that the true story of these cosmic giants is written in a language we have only just begun to learn. A final possibility ventures beyond the edge of known physics, into a realm where the fundamental rules of the universe itself might have been different. When all conventional explanations strain against a paradox, scientists must consider exotic solutions rooted in new physical principles. Perhaps in the extreme density and temperature of the infant cosmos, our understanding of gravity itself breaks down. Some theoretical models suggest that general relativity, while incredibly successful in our local universe, may require modification under such extraordinary conditions. One speculative idea involves the concept of gravitational leakage. If our universe contains more than the three spatial dimensions we experience, gravity could be far stronger in the early universe, seeping into these hidden realms and allowing for a dramatically accelerated collapse of primordial gas clouds. In this scenario, forming a massive black hole seed would not be a rare event, but a natural and efficient process dictated by a richer, more complex fabric of spacetime. Another proposal examines the very constants of nature. What if the strength of gravity or the speed of light were not truly constant, but varied in the universe's first moments? A subtle change in these foundational numbers could lower the barrier for black hole formation, making the rapid emergence of giants not just possible, but inevitable. These are not ideas with direct observational evidence, but they represent the necessary creative leaps that occur at the frontiers of science. They demonstrate that the puzzle of early supermassive black holes is more than an astronomical curiosity. It is a potential signpost pointing toward a deeper layer of physical reality. These cosmic giants become natural laboratories, their impossible presence challenging us to rewrite the textbooks. The true answer may not lie in choosing one of these five paths, but in discovering a new, unforeseen mechanism that combines elements from several. How then do we move from these grand theoretical possibilities to tangible proof? The next great leap requires translating these ideas into observable signatures that our most powerful telescopes can hope to see. The distant glow of a primordial quasar is more than just ancient light. It is a cosmic time capsule holding the secrets of its creation. To unlock it, we must learn to read its spectral signature, the unique fingerprint imprinted on its light after its epic journey across the cosmos. This is the work of the world's most powerful telescopes, transforming brilliant points of light into detailed biographies of these infant giants. The James Webb Space Telescope has become our ultimate time machine, its infrared eyes peering into an era just 400 million years after the Big Bang. There it has found fully formed black holes already weighing 1 billion suns, their brilliant quasars shining from within surprisingly mature galaxies. This discovery pushes the clock back even further, demanding that whatever process built these monsters was not just efficient, but astonishingly swift. How do we weigh a black hole we cannot see? The answer is written in the speed of the gas swirling around it. By analyzing the subtle shifts in the quasar's light, a technique known as spectroscopy, astronomers can measure the velocity of this material. Just as the planets in our solar system move faster the closer they orbit the Sun, the speed of this cosmic gas reveals the immense gravitational pull and therefore the mass of the invisible black hole at the center. These measurements are the ultimate reality check for our theories. They tell us exactly how massive these objects were at a given moment in cosmic history, setting a strict timer for their growth. Simultaneously, other instruments study the galaxies that host these brilliant engines. Vast reservoirs of cold molecular gas, the raw fuel for star formation and black hole growth, have been detected in these early systems. The dynamics of this gas are critical. Is it turbulent and unsettled, easily pushed away by stellar winds, or is it flowing smoothly and efficiently into the galactic core like a river feeding a waterfall? Observations increasingly suggest that the most active quasars live in galaxies where the conditions are just right for this efficient fueling, often following periods of galactic collision or intense starburst activity that funnels material inward. Each new dataset acts like a key, unlocking one door while closing another. The detection of such massive black holes in very small galaxies, for instance, challenges the merger theory, which predicts the black hole and its host galaxy should grow in lockstep. The light from the earliest quasars often shows they were feeding at or even above the Eddington limit, giving vital support to the super-accretion model. Yet, the sheer number of these early giants also suggests that the direct collapse seed theory must be at play in at least some environments, providing that crucial head start. The emerging picture is not one of a single, neat solution, but of a complex cosmic ecosystem. Different pathways to greatness may have operated in tandem, depending on the specific conditions of a galaxy's birth. In the dense, chaotic nursery of the early universe, some black holes may have been born large from direct collapse, while others gorged themselves on sudden feasts of gas, and still others grew through a series of rapid mergers. The mystery is no longer about finding one answer, but about understanding the intricate dance of physics that allowed for all these possibilities to create the cosmic rulers we observe today. These digital universes run not on telescopes, but on some of the world's most powerful supercomputers. Here, astrophysicists can rewind time to the Big Bang, sprinkle a virtual cosmos with dark matter and primordial gas, and then fast forward, watching the laws of physics play out over billions of virtual years. These are not simple animations, they are intricate digital laboratories where every particle of gas, every burst of starlight, and the relentless pull of gravity are calculated with immense precision. To understand how a supermassive black hole grows, you must first understand the galaxy it lives in, and these simulations provide that grand, dynamic stage. They weave together the complex physics of gravity, the fluid dynamics of cosmic gas, the explosive energy of star formation, and the blinding radiation that pours from an active black hole. By changing the initial recipe, scientists can perform cosmic experiments. What happens if the first stars form differently? How does a galaxy merger alter the flow of gas to the center? Does a black hole born from direct collapse grow faster than one built from mergers? Each simulation run is a unique test of a theoretical pathway, a digital experiment that would be impossible to conduct in the real world. State-of-the-art projects like Illustris TNG and FIRE have become virtual observatories, generating synthetic skies that can be directly compared to the data from Hubble and the James Webb Space Telescope. One of the most critical insights from this work is the concept of feedback. A growing black hole is not a passive vacuum cleaner, it is an active and powerful engine. As it feeds, it floods its surroundings with intense radiation and can launch jets of plasma at near light speed. This energy heats the surrounding gas, pushing it away and effectively shutting off the black hole's own food supply. It is a self-regulating process, a natural thermostat that prevents runaway growth. For a black hole to become supermassive in the early universe, it had to find a way to overcome this feedback, either by consuming gas so rapidly that it overwhelmed its own energy output, or by existing in an environment so dense and turbulent that fresh fuel was constantly being forced inward. The simulations show that this delicate balance between feeding and fasting is the true key to the mystery. They help translate theoretical ideas into observable predictions, suggesting, for instance, that a galaxy hosting a direct collapse black hole might have a unique chemical signature, or that a black hole in a super Eddington state should have a specific pattern in its emitted light. By comparing the virtual universe to the real one, we can see which of our cosmic stories holds up and which must be rewritten. A black hole's journey to greatness is not a solo mission, but a story written by its entire galactic neighborhood. Its growth is an intimate dance with the swirling city of stars it calls home, a partnership so profound that the final mass of the dark heart is often perfectly mirrored by the size of the galaxy's own central bulge. This cosmic correlation is a powerful clue, suggesting that black holes and their galaxies grew up together, their fates intertwined across billions of years. The environment is everything. Imagine two seeds planted in different soils. One falls in rich, well-watered earth, while the other lands on barren rock. Their growth will be vastly different, even if they are genetically identical. For a supermassive black hole, the richness of the soil is measured in cold, dense molecular gas. This is the raw fuel for both star formation and black hole accretion, and in the early universe, galaxies were overflowing with it. These primordial systems were not the grand, stately spirals we see today. They were compact, turbulent, and constantly bumping into one another. This chaos was the perfect nursery for rapid growth. When two young galaxies collided, their orderly structures were violently shaken. The resulting gravitational turmoil acted like a cosmic funnel, efficiently channeling vast rivers of gas directly toward the center, delivering a feast to the waiting black hole. But even without a dramatic collision, the internal architecture of a galaxy plays a crucial role. A massive stellar bar, a dense structure of stars cutting through the galactic center, can act like a conveyor belt, slowly and steadily draining gas from the outer regions and pushing it inward. The very spin of the infalling gas is also critical. Gas with too much angular momentum will simply orbit forever, like water swirling around a drain but never going down. For a black hole to feed, something must rob that gas of its spin, allowing it to finally cross the event horizon. Dense clusters of stars, magnetic fields, or the gravitational shock of a merger can all provide the necessary braking force, turning a stalled reservoir into a direct delivery system. This complex interplay of factors explains the great diversity we observe. A black hole born in a quiet, isolated galaxy with little gas may remain a modest seed for eons. Yet an identical seed placed in a gas-rich environment undergoing frequent interactions could be transformed into a brilliant quasar in a relatively short cosmic time. The giants of the early universe did not simply break the rules of physics. They were born into a world where the rules of engagement were fundamentally different, a context of abundance and chaos that provided a perfect pathway to power. This brilliant energy, however, carries a self-destructive seed. A black hole's most powerful feasts trigger a natural shutdown system, a cosmic conversation between the devourer and its home. This process is known as feedback, and it is the ultimate regulator of growth. As vast quantities of matter spiral inward, they are heated to incredible temperatures, flooding the surrounding space with intense radiation. This radiation slams into the remaining reservoirs of cold gas in the galactic core, heating them so powerfully that they cannot condense and fall inward. The black hole effectively burns its own food supply. In more extreme cases, the system can launch colossal winds, blasting gas out of the galaxy entirely at thousands of miles per second, or focus energy into narrow, piercing jets that carve through interstellar space. These outflows can clear entire regions of the vital fuel needed for both future black hole meals and for the birth of new stars. This is why most supermassive black holes, including the one at the heart of our Milky Way, spend the majority of their lives in a quiet, dormant state. Their own brilliant power creates a desert around them, forcing a long fast after every large meal. For the early universe to build its giants so quickly, this feedback loop had to be overcome. How could a black hole continue to feed when its own energy should be pushing the dinner plate away? One possibility is that the conditions were simply different in the cosmic dawn. Galaxies were so overwhelmingly dense with gas that this primordial fuel could absorb the intense radiation without being completely blown away. The pressure from the surrounding material was so immense that it could force gas inward against the outward push of the black hole's energy, like trying to shout down a hurricane. In this environment, feedback was less about stopping growth and more about moderating it, creating a sustained, high-pressure inflow that allowed for rapid, continuous building. Another fascinating idea involves the geometry of the feast itself. Perhaps the gas did not fall in from all directions, but was delivered in a very specific way. Imagine a dense, cold stream of gas flowing smoothly into the center, shielded from the black hole's intense radiation by an outer cocoon of material. This configuration could act like an insulated pipeline, delivering fuel directly to the event horizon while the blinding energy escapes through less obstructed channels above and below. This would allow the black hole to gorge itself while its disruptive energy vents harmlessly into space, a perfect setup for Eddington accretion. The key to understanding these ancient giants lies in this delicate balance. Their incredible growth was not just about the availability of food, but about mastering the art of eating without destroying the kitchen. Their rise to power required a perfect, and likely temporary, alignment of cosmic conditions where the rules of self-regulation were suspended or rewritten. This dance of creation and destruction, of feeding and feedback, is written into the very fabric of every galaxy we see today, a lasting signature of how the universe learned to control its most powerful engines. Another pathway to these cosmic giants may lie in the very first moments of everything, before the first stars flickered to life, before galaxies even began to coalesce. The universe was a seething, hyper-dense soup of energy. In that primordial chaos, some cosmologists suggest the seeds for supermassive black holes were already sown. These would not be the remains of dead stars, but ancient relics born from the raw fabric of the newborn cosmos itself. They are known as primordial black holes. The theory proposes that in the first second after the Big Bang, tiny quantum fluctuations in density, microscopic wrinkles in spacetime, could have been stretched to enormous scales by a period of rapid inflation. In regions where the density was exceptionally high, gravity could have won a sudden, decisive victory, causing pockets of space to collapse directly into black holes. This process could have created a vast population of these objects, ranging in size from smaller than an atom to many times the mass of our Sun, all within the blink of a cosmic eye. The most massive of these primordial seeds would have had a tremendous advantage. A black hole born with 1,000 solar masses, or even 100,000, would already be a gravitational titan in a universe of scattered gas. It would immediately begin pulling in the surrounding material, starting its growth journey hundreds of millions of years before the first stellar black holes could even form. This head start could be the crucial key to solving the timing paradox, providing ready-made giants that simply needed to be fed. The evidence for this idea, while speculative, is growing more intriguing. The detection of gravitational waves from merging black holes by observatories like LIGO has revealed black holes of masses that are somewhat unexpected. Some of these could potentially be explained if they were primordial in origin, ancient fossils finally making their presence known through cosmic collisions. Furthermore, the relentless hunt for dark matter raises a fascinating possibility. Could some, or even all, of the invisible substance that binds galaxies together actually be a vast swarm of these primordial black holes? While current observations have largely ruled out them being the primary component of dark matter, the door remains open for a population of asteroid mass or larger primordial black holes to be hiding in the darkness. Confirming their existence would do more than just explain supermassive black holes. It would open a direct window into the most extreme energies and highest temperatures the universe has ever experienced. It would connect the largest structures we see today to the quantum ripples of the first instant, a profound link between the infinitesimally small and the cosmically vast. This hypothesis challenges us to see these galactic rulers not as products of their time, but as living fossils carrying the imprint of creation itself within their silent, dark hearts. These cosmic crime scenes are billions of years cold, their faint evidence stretched and distorted by an expanding universe. Our most powerful telescopes face a fundamental challenge, a cosmic signal degradation that makes the earliest chapters of this story the most difficult to read. The light from these infant quasars has traveled for over 13 billion years to reach us, a journey so immense that their brilliant beacons arrive as mere whispers. This incredible distance means the signal is not just faint, it is fundamentally transformed. The expansion of the universe itself stretches the light waves, shifting them from the visible and ultraviolet light they were emitted in toward the red and infrared part of the spectrum. It is like listening to a song played on a record that has been slowed down, its pitch lowered into a different key. This is why the James Webb Space Telescope, with its unparalleled infrared sensitivity, is our ultimate tool for this investigation. It is designed to hear the universe's oldest songs in the key they now arrive in. Even with this technological marvel, dust remains a persistent cosmic conspirator. The early galaxies where these black holes grew were often shrouded in thick clouds of gas and cosmic soot. This dust effectively hides the growing black hole from optical and ultraviolet telescopes, much like a dense fog obscuring a lighthouse. We can only infer the engine's presence by the warmth it leaves on the surrounding dust, a telltale glow that again reveals itself only in the infrared. The most frustrating limitation might be one of pure resolution. The central engine of a distant quasar, the region where matter is spiraling into the black hole, is so incredibly small on the sky that it appears as a single, unresolved point of light even to our sharpest telescopes. We cannot see the intricate structure of the accretion disk or the precise mechanisms of gas inflow. It is as if we are trying to understand the inner workings of a car engine by looking at a single, brilliant headlight from a mile away. This fundamental blurriness forces us to rely on indirect clues, like the overall brightness and the color of that light, to piece together what is happening on scales smaller than our own solar system. And then there is the ultimate constraint, the tyranny of the finite speed of light. When we observe a quasar from the universe's first billion years, we are not seeing it as it is today. We are looking at a single snapshot, a baby picture from its infancy. We have no time-lapse video of its growth. To understand its life story, we must observe millions of different black holes at different cosmic ages, and then attempt to connect the dots, assembling a family album from scattered, ancient portraits. This is why the scientific debate remains so vibrant. Each flicker of ancient light can be interpreted in multiple ways. A brilliant quasar could be a direct collapse black hole enjoying its first meal, or a merger remnant in a state of super Eddington accretion, or something else entirely. The data we collect is like a faint, ancient language where the same symbol can have several meanings. Our current evidence is often consistent with more than one of the competing theories, leaving the final chapter of this cosmic mystery still waiting to be written. The search for a single cosmic rulebook has led us to a more complex and beautiful truth. No single theory can claim victory, for the evidence points toward a grand synthesis. The universe, in its infinite creativity, likely employed every tool at its disposal. A primordial black hole seed, born from direct collapse, could have been placed in a perfect cosmic cradle. There, within a gas-rich young galaxy, it might experience its first super Eddington feast during a violent merger, rapidly ballooning in size. Later, as it drifted through the cosmic web, this growing giant could absorb smaller black hole siblings, each merger adding another piece to its final immense mass. This multifaceted growth is not a compromise but a reflection of reality. The diversity of supermassive black holes we see today, from the quiet giants in dormant galaxies to the brilliant quasars of the early universe, simply reflects different chapters in their life stories, each written by a unique combination of these physical processes. The focus of theoretical work has now shifted dramatically. Scientists are not just testing individual ideas, but are building intricate digital universes to see which combinations of mechanisms can reproduce the entire population of black holes we observe, all within the tight constraints of cosmic time. The key variable is the environment. In an isolated, gas-poor galaxy, growth may be slow and steady, dominated by occasional small mergers. But in the dense, chaotic core of a massive protogalaxy, the perfect storm of a large seed, abundant fuel, and frequent interactions could forge a billion solar mass titan in a cosmic blink. This synthetic approach moves us beyond simple explanations toward a richer, more nuanced understanding of cosmic evolution. It reveals a universe where gravity, gas dynamics, and radiation engage in an intricate dance, their steps varying from one galactic neighborhood to the next, weaving together to create the magnificent tapestry of structure we observe across the cosmos. The next decade promises to rewrite our cosmic textbooks, not with new theories alone, but with revolutionary tools designed to see the unseen. We stand at the threshold of a new era in astronomy, where a fleet of next-generation observatories will act as our guides into the darkest corners of space and time. These instruments will move us from interpreting faint whispers to hearing the deep rhythms of the universe itself. The Laser Interferometer Space Antenna, or LISA, is perhaps the most ambitious of these projects. This space-based gravitational wave observatory will consist of 3 spacecraft flying in a perfect triangle millions of miles apart. Unlike its ground-based cousins, LISA will be tuned to the lowest frequencies, the deep bass notes of the cosmos. This is the realm where supermassive black holes sing. When 2 of these giants spiral together in the heart of a distant galaxy, LISA will capture the resulting gravitational waves, allowing us to trace the growth history of black holes through their mergers across cosmic time. It will listen to the collisions that built the very first Titans. Meanwhile, the Nancy Grace Roman Space Telescope will open a panoramic window onto the early universe. With a field of view 100 times larger than the Hubble Space Telescopes, Roman will conduct vast, deep sky surveys. It will not just find a few rare quasars, it will census entire populations of them, identifying the rarest objects from the cosmic dawn, including potential direct collapse black holes in their infancy. By finding these elusive seeds, Roman could finally tell us which birth pathway nature preferred. On the ground, a new generation of extremely large telescopes, with mirrors spanning over 30 meters, will collect more light than ever before. Their immense resolution will allow us to study the gas dynamics in the very first galaxies with exquisite detail, watching how fuel flows toward the center and how black hole feedback affects its surroundings. We will see the cosmic kitchen in action. In tandem with these new eyes and ears, theoretical work is undergoing its own revolution. Supercomputer simulations are growing more sophisticated, weaving together the complex physics of Eddington accretion, dark matter interactions, and the chaotic conditions of the primordial universe. The goal is no longer to support a single theory, but to create a unified model of black hole evolution, one that can account for the incredible diversity we observe. The ultimate breakthrough will come from combining all these signals. This is the promise of multi-messenger astronomy, where a single cosmic event, like a black hole merger, is observed through multiple lenses. Lisa might feel the gravitational shudder, while the Roman telescope sees the flash of light from the accompanying gas, and neutrino detectors catch elusive particles from the violent aftermath. By piecing together these different messengers, we can build a three-dimensional picture of the event, understanding its physics, its environment, and its place in the history of the cosmos. The path forward is not a single question, but a symphony of coordinated discovery. Each new observation will act as a key, unlocking one door while forcing us to close another, gradually narrowing the possibilities until the true story of these cosmic giants is finally brought into the light. This grand cosmic puzzle offers more than just answers. It provides a living classroom for how science truly works. The debate over these giants reveals a process far from settled, a dynamic and ongoing conversation where new evidence can overturn old ideas overnight. Students today have a front-row seat to a genuine scientific mystery, witnessing the same process of questioning and discovery that once shaped our understanding of gravity or evolution. They learn that not all questions have answers yet, and that the universe is still full of secrets waiting to be uncovered. This journey into the unknown is powered by a fusion of disciplines. Unraveling the black hole growth paradox is not a task for astronomers alone. It requires the abstract logic of mathematicians to model new theories, the computational power of computer scientists to run immense simulations, and the ingenious problem-solving of engineers who design the telescopes that act as our time machines. This collaborative effort demonstrates that scientific progress is a team sport, where diverse skills and perspectives combine to push back the frontiers of ignorance. The public fascination with these dark giants is undeniable. Planetarium shows that journey to a black hole's edge, and interactive museum exhibits that let visitors manipulate virtual accretion disks consistently draw crowds, young and old. These encounters transform an abstract concept into a visceral experience, a gateway that sparks curiosity about physics, the nature of space and time, and our place in the cosmos. This engagement is vital, cultivating a society that values evidence, critical thinking, and the shared human endeavor of exploration. The story of supermassive black holes perfectly illustrates the self-correcting and ever-expanding nature of scientific knowledge. Each new observation, whether from a space telescope or a gravitational wave detector, does not simply provide a final answer. More often, it refines the question, revealing deeper layers of complexity and pointing toward mysteries we had not even thought to ask. This endless cycle of discovery and inquiry is what inspires a child gazing at the stars to become the scientist who one day unlocks a new cosmic law, ensuring the journey of understanding continues far into the future. Ultimately, these cosmic giants are more than just gravitational puzzles. They are mirrors reflecting the very limits of human comprehension, their existence at the edge of space-time, where our familiar laws of physics break down, forces a humbling realization. The reality they inhabit is fundamentally alien to our daily experience of time, space, and matter. We are creatures of a moderate world, yet we strive to understand realms of such extreme density that a single teaspoon of black hole material would weigh more than every mountain on Earth combined. This vast disconnect between our intuitive grasp and the universe's true nature is the very challenge that scientific inquiry was built to overcome. The fact that we can detect the shadow of one, measure the mass of another, and theorize about their origins from our tiny planetary outpost is a testament to a profound human capacity. It is the power of reason, of building tools that extend our senses across billions of light years to interrogate the darkness. The unresolved mystery of their rapid growth is not a failure of science, but its very engine. It reminds us that our current understanding is not a final destination, but a single frame in a much longer film of discovery. Each new generation inherits the questions of the last, armed with better technology and sharper theories, pushing the boundary of the known just a little further. In the grand, silent dialogue between human curiosity and cosmic mystery, these black holes are our most demanding and perhaps most rewarding partners. They shrink our worldly concerns to a speck of cosmic dust, while simultaneously elevating the act of asking a simple question into a journey that can span the lifetime of the universe itself. The true test of any cosmic theory lies not in its elegance, but in its ability to withstand the harsh light of evidence. Placing these 5 competing ideas side by side reveals a fascinating landscape of trade-offs, where every potential solution comes with its own unique set of promises and puzzles. The direct collapse model provides the most elegant answer to the timing paradox, gifting a black hole a massive head start that neatly sidesteps the need for impossibly long feeding periods. Its greatest weakness, however, is its reliance on a perfect cosmic cradle. The pristine gas clouds and specific radiation fields required for this direct birth might have been exceedingly rare in the early universe, perhaps too rare to account for the vast numbers of supermassive black holes we observe. If this was the primary path, we should expect to find these ancient seeds only in the most massive and specially conditioned early galaxies, a prediction that next-generation telescopes are now actively hunting. In contrast, the super-Eddington accretion theory offers a thrilling vision of violent, rapid growth that could happen to almost any black hole seed, stellar or otherwise. Its appeal is its dynamism, turning the early cosmos into a buffet of chaotic feasts. The central challenge here is one of sustainability. Can these frenzied feeding episodes last long enough and occur frequently enough to build a billion solar mass giant? The immense energy released during such a binge would likely blow away the surrounding gas reservoir, cutting off the very feast that powers it. For this theory to hold, we must find evidence of black holes caught in this act, their light bearing the unique signature of a meal that defies the standard cosmic diet. The merger pathway builds on the well-established idea of hierarchical growth, where small structures relentlessly combine to form larger ones. It is a comforting, bottom-up narrative. Yet, when applied to the earliest universe, the clock becomes the enemy. The process of black holes finding each other, spiraling together, and finally merging is gravitationally complex and time-consuming. To build a true titan through mergers alone requires a breathtakingly rapid-fire sequence of unions, a cosmic assembly line that must operate with flawless efficiency in an era when the first galaxies were only just beginning to form. This path predicts that the very first quasars should be found in galaxies that show clear signs of recent, violent collisions, a clue that observers are keen to trace. Then we have the more speculative frontiers. Theories involving dark matter or exotic physics boldly confront the gaps in our current knowledge, suggesting that the answer lies not in known astrophysics, but in fundamentally new principles. While they lack direct evidence, their value is immense. They serve as vital reminders that our understanding is incomplete, pushing the entire field to consider possibilities beyond the conventional. They make testable predictions, too, about the behavior of gravity in the infant cosmos or the potential existence of a hidden population of primordial black holes. This comparative exercise makes one thing abundantly clear. The ongoing debate among scientists is not a sign of failure, but a testament to the richness of the mystery. A cosmologist favoring the clean logic of direct collapse, an astrophysicist championing the violent drama of superaccretion, and a theorist exploring the shadows of dark matter are all looking at the same universe through different lenses. Their disagreement is the engine of discovery, with each camp making specific predictions about what our telescopes should find. The mass distribution of the very first black holes, the types of galaxies that host them, and the gravitational wave background from their ancient mergers all hold the key. The final answer is unlikely to be a single winner, but a complex tapestry woven from several of these threads, revealing a universe that used every tool at its disposal to build its masters. The very idea of a star so dense that light could not escape was first proposed in the late 1700s, a speculative concept known as a dark star. It would take the revolutionary framework of Einstein's general relativity to give this notion a mathematical backbone, transforming it from a philosophical curiosity into a potential physical reality. Yet for decades, these dark stars remained largely theoretical, ghosts in the equations of physicists. The turning point arrived in the 1960s with the discovery of quasars, points of radio energy that optical telescopes revealed as the most brilliantly luminous objects in the entire universe. Their incredible compactness and power defied all known explanations involving stars alone, forcing astronomers toward an astonishing conclusion. These cosmic beacons were likely the visible signature of supermassive black holes in a state of incredibly violent feeding, a concept that shifted these objects from mathematical oddities to active, dominant players in the cosmos. As telescope technology advanced, each new instrument peeled back another layer of time. The Hubble Space Telescope, and now the James Webb, have repeatedly found these brilliant quasars at ever greater distances, meaning they existed in an ever younger universe. With each new discovery, the timeline for building a billion solar mass giant grew tighter and more improbable. This relentless push backward by observation has created the central growth timing problem we grapple with today. It is a classic example of the scientific process in action, where new data consistently challenges comfortable theories, forcing a cycle of prediction, observation, and fundamental revision. Our current debate is simply the latest iteration of this endless, collaborative conversation with the cosmos, a conversation where the universe holds all the answers and our job is simply to learn how to ask the right questions. The quest to understand these cosmic giants has shattered the old boundaries of scientific inquiry. Cracking the code of their growth is no longer a task for astronomers alone, but a grand collaborative effort that draws from nearly every corner of modern science. At its most fundamental level, astrophysics meets particle physics in the speculative dance around dark matter, where theorists model how invisible particles could be funneled into a black hole's heart. To test these ideas, we turn to the digital universe. Computer scientists and programmers work with astrophysicists to write the immensely complex code that powers supercomputer simulations, algorithms that must calculate the simultaneous interactions of billions of particles governed by gravity, fluid dynamics, and radiation. These virtual cosmos are our only laboratories for experiments that span billions of years. The tools for this exploration are marvels of modern engineering. Building a telescope like the James Webb requires breakthroughs in materials science to create its delicate, gold-coated beryllium mirrors and its complex sunshield, each component engineered to perform flawlessly in the harsh environment of space. The detectors that capture the faintest whispers of infrared light from the edge of time are themselves triumphs of nanotechnology, designed to be exquisitely sensitive to the slightest energetic whisper. Once the data streams in, the challenge is just beginning. The signals from these distant quasars are buried in a sea of cosmic noise. Data scientists and statisticians develop sophisticated machine learning models to sift through this information, separating the true fingerprint of an ancient black hole from the background static of the universe. Even the seemingly unrelated field of geology finds a voice in this chorus. The way turbulent fluids flow and interact with their surroundings, studied in the context of magma flows or atmospheric patterns, provides powerful analogies for understanding how chaotic streams of cosmic gas might behave as they spiral into an accretion disk. This incredible convergence of disciplines makes black hole research a vibrant meeting ground. It is a place where a particle physicist's equation, a computer scientist's algorithm, and an ENGINEERS Chinese letter instrument must all align to answer a single, profound question. This cross-pollination of ideas is a powerful engine for innovation, as techniques developed for one field are adapted to solve problems in another, pushing the entire frontier of knowledge forward. The collaborative effort to weigh an invisible object 13 billion light-years away exemplifies a fundamental truth of modern science. The most compelling mysteries of our universe can no longer be solved by a lone genius in an isolated field. They demand a symphony of diverse expertise, a testament to the collective power of human curiosity focused on a single, dazzling point in the dark. The profound mystery of these cosmic giants resonates far beyond scientific journals, sparking a public fascination that illuminates our collective curiosity. Media announcements of a new black hole image or a distant quasar's discovery consistently captivate global attention, transcending cultural and linguistic boundaries. This widespread engagement is not passive. It is an active participation in the process of discovery. Citizen science initiatives, where thousands of volunteers help classify galaxies or analyze telescope data, transform everyday individuals into collaborators in this grand cosmic census. Public lectures on these dark hearts of galaxies routinely fill planetarium domes and university halls, a testament to a deep-seated desire to understand our place in the vast scheme of things. This broad engagement creates a vital feedback loop, generating public support for the fundamental research that drives these discoveries while simultaneously fostering a more scientifically literate society. The visual drama of these objects is a powerful gateway. Artistic renderings of swirling accretion disks and the now iconic image of the glowing ring with a dark shadow at its center make an incredibly abstract concept suddenly tangible. These visuals appear everywhere, from immersive museum exhibits that transport you to the edge of an event horizon to the imaginative landscapes of science fiction films and literature. They provide a crucial anchor, a way for the human mind to grasp the ungraspable. This collective captivation demonstrates something essential about our species. Even in an age of advanced technology, the most fundamental questions about the nature of space, time, and our cosmic origins continue to hold a profound and universal power. The relentless pursuit of invisible giants has, time and again, gifted us with tools that reshape our own world. The extreme technological demands of black hole research consistently generate revolutionary spin-offs, transforming our daily lives in unexpected ways. To capture the faintest whisper of light from a 13-billion-year-old quasar, engineers must push detector technology to its absolute limit. This drive for sensitivity has produced exquisitely precise sensors that now form the heart of advanced medical imaging machines. The same fundamental physics that allows a telescope to see the shadow of a black hole enables a hospital scanner to peer non-invasively into the human body, detecting illnesses at their earliest, most treatable stages. These sensors also find critical roles in airport security systems, identifying hidden materials with incredible accuracy, and in global environmental networks, monitoring pollution levels and the health of our planet with a watchful eye born from the stars. The challenge does not end with seeing, it extends to thinking. Simulating the chaotic dance of two merging black holes is one of the most computationally intense tasks ever attempted. The sophisticated algorithms developed to model the warping of spacetime and the behavior of superheated plasma have proven equally powerful for solving complex problems here on Earth. Aerospace engineers use these very same computational techniques to simulate the flow of air over a wing, designing more efficient and safer aircraft. Financial analysts apply them to model the turbulent, unpredictable flows of global markets. Even the automotive industry leverages this cosmic code to improve the aerodynamic design of cars and to crash test them in virtual environments, saving immense time and resources. This technological transfer is a story of silent, profound collaboration. The incredibly precise atomic clocks required to synchronize a global network of telescopes for very long baseline interferometry are the same timekeepers that form the bedrock of our modern global positioning system. Without that relentless pursuit of chronological perfection for astronomy, the pinpoint navigation in your smartphone and the stable synchronization of the entire internet would be impossible. Even the machine learning algorithms first honed to pick a distant galaxy's subtle signature out of a sea of cosmic noise are now deployed to diagnose diseases from medical scans, filter spam from your email, and power the recommendation engines that suggest your next favorite film. This recurring pattern reveals a deeper truth about the nature of discovery. Investing in fundamental, curiosity-driven science, even when its goals seem impossibly distant, is not a luxury. It is a seedbed for tomorrow's indispensable technologies. The quest to understand a dark heart at the edge of time has, again and again, returned the light of innovation to illuminate our own world. Their story begins not with a single event, but as a grand, unfolding epic written across 13.8 billion years. To understand the shocking speed of these giants, we must first place them within the complete timeline of the cosmos, from the first flash of existence to the structured universe we see today. Moments after the Big Bang, the universe was a formless, seething sea of energy, expanding and cooling at an incredible rate. A brief period of violent inflation stretched space itself, smoothing out the cosmos and planting the tiny quantum seeds for all future structure. As it continued to cool, particles coalesced into the first atoms, primarily hydrogen and helium, and the universe became transparent for the first time, releasing the cosmic microwave background radiation we can still detect today. This ushered in the cosmic dark ages, a period of profound silence and shadow lasting hundreds of millions of years. The universe was a vast, featureless expanse of neutral gas with no stars, no galaxies, and no light to break the endless night. The end of this dark epoch was a revolution. Within the densest knots of the cosmic web, the first stars ignited. These were not like the stars of today. They were colossal behemoths, hundreds of times more massive than our Sun, burning fiercely and dying young in spectacular supernova explosions. Their light began the process of reionization, tearing apart the neutral hydrogen fog and flooding the cosmos with ultraviolet radiation, a process that cleared the haze and made the universe transparent once more. It is against this backdrop of first light that the supermassive black hole mystery truly deepens. The first galaxies were assembling from these primordial building blocks, yet when we look back with our most powerful telescopes, we find that supermassive black holes were already there, shining as brilliant quasars from within these infant galactic systems. Their presence so early is like finding a fully formed adult in a nursery of newborns, a sign that their growth was not just rapid, but deeply intertwined with the very birth of galaxies. This co-evolution is the key to the entire cosmic story. A growing black hole is not a passive passenger, it is an active architect. Through the immense feedback of its radiation and outflows, it can heat or expel the gas in its host galaxy, effectively shutting down the very star formation that built its home. This creates a self-regulating cycle, a cosmic dialogue between the dark heart and its stellar city. In the early universe, this feedback was a dominant force, carving out the inner structures of galaxies and setting the stage for their future evolution. As the universe aged and expanded, the raw materials for growth became scarcer. Galaxies moved further apart, and the chaotic mergers that funneled gas to their centers grew less frequent. The brilliant quasars of the cosmic dawn slowly faded, their epic feasts giving way to a long, quiet maturity. The supermassive black holes we see in galaxies today are mostly dormant, their immense power hidden, their growth largely complete. This grand timeline reveals a profound connection. The physics that governs the collapse of a single gas cloud also dictates the formation of a billion solar mass giant. The evolution of a supermassive black hole is a direct reflection of the evolution of the universe itself, from a hot, dense beginning to a structured, diverse present. By tracing their growth, we are not just studying exotic objects, we are reading the autobiography of the cosmos, a story written in gravity, light, and time. One of the most persistent images is that of a cosmic vacuum cleaner, an infinitely hungry drain swallowing everything in its path. The reality is far more nuanced and far less efficient. A black hole's gravitational pull is immense, but to actually fall in, material must first lose nearly all of its angular momentum, the spin that keeps it in a stable orbit. Most gas and stars will simply whirl around the void for eons, never getting close to the point of no return. Accretion, the process of growth, requires a specific and delicate choreography where gas clouds collide, shed their energy, and slowly spiral inward. This is not a relentless suction, but a slow, cosmic dance where the music often stops before the final step is taken. The idea of a black hole swallowing stars whole is another dramatic exaggeration. While such stellar disruptions do occur, they are rare cosmic snacks. The primary diet for a growing supermassive black hole is not stars but vast, diffuse clouds of gas and dust. This material can be gradually drawn into the accretion disk, where friction heats it to incredible temperatures, causing it to glow brilliantly before it vanishes. This steady, gradual accumulation of interstellar gas is the true engine of growth, a slow and steady feast that builds a giant over cosmic epochs. We must also recalibrate our sense of time. When we say a black hole grew rapidly, we mean it on a cosmic scale. A growth spurt that seems impossibly fast to us still unfolds over hundreds of millions of years. This was not an instantaneous event, but a sustained period of high activity within the turbulent nursery of a young galaxy. The black hole and its host galaxy are locked in a complex symbiotic relationship. It is not a simple story of a monster destroying its home. The immense energy released by an actively feeding black hole can indeed blast away gas, quenching star formation and limiting its own future growth. Yet, these same powerful outflows can also trigger the collapse of gas clouds in the galactic outskirts, sparking new waves of star birth far from the center. This intricate feedback loop means the black hole acts as both a regulator and a catalyst, its power shaping the very galaxy that cradles it. Clearing away these myths is essential. It allows us to see these objects not as mindless destroyers, but as dynamic components of a cosmic ecosystem, following physical laws that are as precise as they are profound. This professional balancing act reveals science in its purest form. Astronomers investigating the supermassive black hole growth mystery do not simply choose a favorite theory and defend it. They operate like master detectives, assembling a case from every available clue, no matter how faint or contradictory. Their primary tool is observational data, the hard evidence collected by our most powerful telescopes. Each flicker of light from a distant quasar, each precise measurement of a star's orbit, is a piece of the puzzle. But raw data alone is silent. It requires interpretation through the lens of theoretical modeling, where physicists use mathematics to build possible explanations for what they see. These models are then stress-tested against reality using immense computer simulations, virtual universes where different growth scenarios can play out over billions of years. Each line of evidence has its own strengths and its own blind spots. Observations provide the ultimate reality check, but are often limited by distance and resolution. Theoretical models offer elegant solutions but can be based on assumptions that may not hold true. Simulations can reveal unexpected emergent behaviors, but are only as good as the physics programmed into them. A professional astronomer must hold all these approaches in mind simultaneously, weighing their conflicting implications without prematurely committing to a single story. This requires a unique blend of creativity and skepticism. Researchers must be imaginative enough to propose radical new ideas, like dark matter accretion or super Eddington feeding, yet disciplined enough to subject those same ideas to the most rigorous possible tests. They cultivate a productive discomfort, a state of mind that is never fully satisfied with the current explanation. The vibrant, often heated debates that occur at scientific conferences and in journal articles are not a sign of dysfunction. They are the engine of progress, a collective effort to poke holes in every argument until only the most robust conclusions remain. This process is inherently self-correcting. A theory that seems elegant and compelling one year can be overturned by a single, unexpected observation the next. The entire community remains ready to revise its understanding, guided not by preference but by evidence. This methodological sophistication is what allows science to navigate the most profound mysteries, moving gradually from confusion to clarity, one careful step at a time. Their gravitational pull extends far beyond the realm of physics. firmly anchoring them in our collective imagination. Supermassive black holes have become modern mythologies, appearing not just in scientific papers, but in blockbuster films and classic literature as gateways to other universes or as metaphors for the ultimate unknown. The very phrase black hole has been adopted into everyday language, used to describe everything from a financial loss to a mysterious situation, demonstrating how deeply this cosmic concept has shaped our way of speaking about the world. Artists are endlessly drawn to their paradoxical nature, creating works that range from breathtakingly accurate visualizations based on telescope data to abstract paintings that explore themes of infinity, silence, and gravitational longing. This widespread cultural resonance points to something fundamental. These dark giants tap into a universal human curiosity about the void, the edge of understanding, and our own fragile place in a vast and often incomprehensible cosmos. They serve as powerful symbols for the limits of knowledge and the awe that comes from confronting something truly greater than ourselves. Their depiction in stories and art is rarely just about the object itself, but about our relationship to the mysteries it represents. A black hole in a film might symbolize an inescapable fate or a journey into the subconscious, while in philosophy, it can challenge our most basic assumptions about reality, time, and existence. This duality makes them unique. They are real physical phenomena studied with mathematical precision, and they are potent cultural icons that speak to our deepest hopes and fears about the universe. Their story is not only written in the light of distant quasars, but in the creative expressions of humanity itself, proving that our quest to understand the cosmos is as much an artistic and philosophical endeavor as it is a scientific one. The journey into these cosmic mysteries does not end when the screen fades to black. For any mind sparked with curiosity, a universe of deeper exploration awaits, all accessible from the comfort of your own home. Reputable websites maintained by NASA and the European Space Agency are your front row seat to the latest discoveries, offering press releases, stunning images, and detailed articles that translate complex research into understandable stories. Major research universities often share the groundbreaking work of their astrophysics departments online, providing a direct line to the scientists who are actively piecing this puzzle together. If you prefer to hold the cosmos in your hands, popular science books by authors like Kip Thorne, Brian Greene, and Jana Levin weave the science of black holes and relativity into compelling narratives, guiding you through the concepts without requiring a degree in physics. For those who learn best by seeing, documentaries from series like PBS Nova and BBC Horizon bring these invisible giants to life through breathtaking animations and interviews with the researchers on the front lines, making the abstract tangibly real. A visit to a local science museum can transform your understanding, as planetarium shows project you across the galaxy, letting you float at the edge of an event horizon in a full-dome immersive experience. For a more structured path, online learning platforms such as Coursera and edX offer courses from leading institutions on topics ranging from introductory astronomy to the intricacies of general relativity, allowing you to learn at your own pace. Perhaps the most thrilling opportunity lies in becoming an active participant in this grand investigation. Citizen science projects, most notably the Zooniverse platform, invite you to roll up your sleeves and contribute to real research. You could be the one to help classify distant galaxies from telescope surveys or analyze the light curves of quasars, directly aiding astronomers in their quest to understand how these cosmic giants grew. The secrets of the universe are no longer locked away in elite laboratories. They are waiting in the digital commons for anyone with a thirst for knowledge and a connection to the web. Our journey through the competing theories of cosmic growth reveals a universe far more creative than we ever imagined. We have ventured from the possibility of black holes born large from primordial collapse to visions of them gorging in feeding frenzies that shatter their own dietary limits. We have traced their potential assembly through rapid fire mergers and even dared to consider the influence of dark matter or exotic new physics. Each pathway offers a compelling, yet incomplete, key to the same profound lock, the timing paradox of giants in the cosmic nursery. This vibrant debate is not a sign of scientific failure, but a brilliant display of its true strength. Our understanding evolves not through declarations, but through this very process of proposal, challenge, and refinement. Every new observation from a space telescope, every subtle signal from a gravitational wave detector, acts as a vote for or against these theoretical narratives, gradually steering us closer to a unified truth. The progress of the last few decades alone is staggering, transforming these objects from mathematical curiosities into observable, measurable phenomena whose origins we can now seriously debate. While the full story of their rapid ascent remains shrouded in the haze of the early universe, the very act of grappling with this mystery illuminates a greater truth. The cosmos is a place of endless wonder, where every answered question simply reveals a deeper layer of beautiful complexity. The existence of these ancient giants continues to challenge our models and inspire our tools, a constant reminder that the universe holds profound secrets not as punishments for our ignorance, but as invitations for our curiosity. Our exploration does not end here, it merely pauses, waiting for the next generation of telescopes and the next brilliant mind to pick up the thread and continue the greatest story ever told.